So exponential decays occur when a quantity decreases by the same percentage in a fixed time period. And that the value of the quantity that repeatedly decreases to half its value with each halving is occurring in a time called half-life. So a lot of the problems that involve half-life have to do with like for example, radioactive materials, and you see some examples listed here. Um, the other types are medical problems, talking about the blood alcohol content in the body, in the bloodstream, talking about um, the um, taking a drug and how much of that medication is left in the bloodstream after a certain time period. So in this discussion here, it's showing you that in the half-life, it tells you of this plutonium 239 is 24,000 years. And if it was deposited at a nuclear waste site, it would decline to half its value. So if it was 100 pounds, then it would become 50 pounds, but it takes 24,000 years. And then after 48,000 years, it would become 25 pounds. So it's taking that 24,000, the number of years, and every time that many years has passed, it goes to half its value. So it says, let's generalize this. So we can kind of see the pattern that's emerging. So what is happening? So in general, I'm going to say, well, what's happening, what I see here, the pattern that's emerging, is that I take half and then I raise it to the number of half-lives, which you can find by taking the time and dividing by the half-life. And then I multiply it by the original amount, which in this case is 100 pounds. And then I'll get that future amount. So when I see in this particular case, well, the time is 72,000. It was 24,000. It was 48,000, then 72,000. So how many years afterwards, I take that quantity and I divide it by the half-life. So in this case, this is how I would write it. But in general, if you flip to the next page, you're going to see the formula here. So it's the new value is equal to the initial value times 1/2 raised to the t over capital T half. So, and I want to point out that on the formula sheet, this formula looks like this, where lowercase t stands for the time and the uppercase T stands for the half-life. And then we have the Q, and this is going to be that future amount, or you can say the new value. And then you have Q sub 0. So whenever you have a sub 0 on a variable in math, it means the initial. It's the initial value or the initial amount. And so we'll have this 0.5, or you can use the fraction 1/2. It doesn't matter. So on the formula sheet, you're going to see this in one of those boxes right next to the doubling time formula. And so it says, in this example, it says radioactive carbon-14 has a half-life of 5,700 years. It collects in organisms only while they are alive. Once they are dead, it only decays. And it says, what fraction of the carbon-14 in an animal bone still remains 1,000 years after the animal dies? So this phrase, what fraction, is the same as saying what factor. And so you're looking for in this formula, so either 0.5 or 1/2, you're looking for this portion of the formula. Let me highlight it. So they don't give us the initial amount. It's just asking by what fraction or what factor that would we have to multiply by. So if we calculate this out, just this portion, the time is 1,000. And the half-life, according to the problem, is 5,700. So I'm going to put this in my calculator and see what I get. So I'm going to put in 1/2. I'm going to use this caret symbol. And then if you have the superscript where it has this flashing cursor here, you can just type in the 1,000 divided by 5,700. If your calculator displays it differently with the caret symbol, then you have to surround this numerator with parentheses. So I get 0.885. I'm going to round to the thousandth place. And here, let me show you the other display in the calculator. So some calculators display the caret symbol like this. So if it does, you have to surround that exponent with parentheses. Otherwise, you're going to get the incorrect answer. So let's write down that answer here. So I can write down 0.885, I'm rounding it, or you could, if you change that decimal to a percentage, you could say that 88.5% of the original carbon-14 remains. So now continuing with the next problem, it says, well, if an animal bone had 1 kilogram of carbon-14, what amount remained after the 1,000 years? So I would say I would use this formula from my formula sheet, and I just calculated out this portion. This portion we just calculated out. But now they're giving us the amount, so I'm going to put that here. This is the original amount, Q sub 0. So it tells you if this was the original amount of carbon-14, what remains. So when I multiply this, 1 times the 0.885, I'll be 0.885, and then my units here will be kilograms. Let's take a look at another example. And this time I'm going to look at this one with the half-life of the drug in the bloodstream. So it says, what fraction of the original drug dose remains in the bloodstream in 1 day? And it tells you that this drug has a half-life of 4 hours. So again, you have to pay attention in the MyLab math. Is it asking you for what fraction remains, or is it asking you how much of the item is still present, or what's the future amount? So this one, again, it's saying what fraction remains. And so it's this part of the formula that I'm going to use. Now, and it tells you in this problem that the lowercase t and the capital T have to have the same units of measure. And so here, the half-life, or the capital T, is in hours, and the time is in days. So I need to put them in the same units. So 1 day is the same as 24 hours. So I'm just going to switch everything to hours. You could switch everything to hours, or you could switch everything to days. And let's put the 24 hours. And I'm showing you the units here because I want to show you what's happening with those units. They're going to, you have to have them in the same units so that they cancel out. And so this would end up being, I would rewrite it as 1/2 to the 6th power. And then if I wanted to keep this as an exact value, so does the answer do we want it in a decimal form, or we want it in an exact value? the 6th power in the exponent applies to both the numerator and denominator. 1 to the 6th would be 1 times itself 6 times, or it would just be 1. And 2 to the 6th would be 64. So 1/64th, or writing it in a decimal, if you put it in the calculator, you end up with this, which would be 1.56% of what we started with. And then it says, if you took 800 milligrams of this drug, how much is present in your bloodstream after the day? So again, it's this formula. And this time I know the amount I started with. This is Q sub 0. And I want to find Q. So I'm going to put in 800 milligrams. And then I'm going to put in the 24 divided by 4. The 24 is the 1 day. So this is my lowercase t. And in the problem up above, it told me the half-life was 4. So now let's put this in the calculator and see what we get. Now, I would suggest that you put this all in one step in the calculator. So put in the 800, because you don't want to make the mistake of saying, oh, 800 times a half, well, that's 400, and then I'll raise it to the 6th power. That's not going to be correct, because you have to remember the order of operations. The order of operations say that I have to do the parentheses, exponents, multiply, divide, add, subtract. So it's that PEMDAS. So you have to do the exponent first before you're going to do the multiplication. And so if you just put it in your calculator, the calculator will do the order of operations in the correct order. So it's going to take the 1/2 and raise it to the 6th power and then multiply by 800. So I end up with 12.5. Now all the time you want to make sure you put your units on your answer, the hours divide out, and you're left with milligrams. So this would be the answer here. Now, in the last discussion here, it talks about this is talking about the half-life of caffeine in a healthy individual is about 5 hours. So when you drink a cup of coffee or soda or tea that has caffeine in it, the body metabolizes it in about 5 hours. Now, it could vary from person to person, but they're saying an average healthy individual, 5 hours. So it says, here you drink a cup of coffee. It has 95 milligrams of caffeine, and they've given you this model. So where did they get this? Well, they took that formula and then they substituted in 5 for the capital T. And they substituted in 95 milligrams for the initial amount. So that's all they've done so far. So this is the model. So when it asks you for a model, and you'll see that coming up in chapter 9, that's what you're looking to get. Now it says, well, fill in this using that model. So let's grab the calculator and let's start filling this in. So on the calculator, I'm going to put in 95, 1/2, and then the caret symbol, and then I put in the value of T. So all I'm doing, the hours relates to the T. So with 0, well, that's the initial amount. I could have done that without. This is the initial amount. The units would be milligrams, and I'll write it for this first one, but then we will assume the rest are all milligrams. Now, I'm going to show you a shortcut. On the calculator, instead of retyping this, you can hit second and then the enter button, and then you can left arrow over and change this. So I can change it to 5. After 5 hours, well, it decreases by half the amount. And so now I've done the whole table. I've completed it by using that method in my calculator. And it says, according to this model, will the caffeine ever completely leave your system? And according to this model, it wouldn't. It cuts the number in half every 5 hours, but that it will never end up getting to 0 exactly. It'll get very close to 0. And is this what happens in real life? Well, It's pretty accurate for the first half, but the body eventually does get rid of that caffeine.